Coming together is a beginning, keeping together is progress, working together is success. Edward Everett Hale. As we saw in the previous chapter, bounded contexts are mere mental models. In order to communicate these to others, we use an ubiquitous language. As people, we use mental models to solve problems, and bounded contexts are the preferred way to express that. However, even though bounded contexts, much like mental models, can evolve independently, they do not exist in a vacuum. For such models to have any use, they must integrate and interact with other models. The same applies to bounded contexts. As a consequence, bounded contexts that interact with each other have touch points. In computer science, these are usually known as contracts. But what is the most effective way to enact such contracts? The answer to this question is as old as the first engineer to set foot on the planet. It depends. The natural question then follows. It depends on what? Domain-driven design depends on the nature of the collaboration between the teams making the integration. It depends on the people making it. With this in mind, DDD classifies 3 different types of collaboration. 1. Cooperation, 2. Customer-supplier, and finally 3. Separate ways. Equipped with the knowledge on the different types of collaboration, DDD suggests several patterns to address them. During this video, we will only address the first 2 collaboration types and discuss the patterns used to deal with them. In the next video, we will continue with the final type of collaboration and also mention a few tools to help document projects, such as context maps and C4 diagrams. My opinions and the final conclusion will also belong in the next video. We already have a lot to cover, so let's finally start. The first collaboration type is cooperation, which happens when the teams responsible for the integration of the bounded contexts have a good level of communication and are willing to compromise accordingly. This applies when only one team owns both bounded contexts, or when the teams involved heavily depend on each other to achieve success. The 2 design patterns that best suit such a relationship type are 1. Partnership, and 2. Shared kernel. In the partnership pattern, the teams owning the different bounded contexts are at equilibrium. There is no power imbalance where one team dictates terms to the other. This pattern works best when both teams have strong collaboration practices, there are clear boundaries between their bounded contexts, there is a clear shared domain language for communicating, working on the intercepting parts of their bounded contexts is mutually beneficial, and when the problem being solved is stable. On the other hand, if the teams do not trust each other, the bounded contexts they work on have conflicting goals, such as speed versus consistency. There are communication issues caused by geographical location or culture. The problem being solved changes constantly, or there are unequal contributions to the solution, then this pattern is likely to fail. Sometimes subdomains are big enough to require multiple bounded contexts for their correct modeling. In such scenarios, it is normal for some of the bounded contexts within the subdomain to share some amount of functionality. So the natural question arises, how do you model this shared functionality? Domain-driven design defends that in such cases, you can use a shared kernel, a bounded context shared with all the other bounded contexts. An example of a possible case for a shared kernel is an authorization bounded context, as seen in this figure. It is important to note that shared kernels effectively couple the participating bounded contexts. A change to the kernel needs to be monitored in the other contexts, as failure to do so will result in the participating bounded contexts using an outdated version of the shared kernel, resulting in inconsistencies and data corruption. Furthermore, the bigger the surface area of said kernel, the more likely we are to incur in cascading changes, like the shotgun surgery anti-pattern. And that's not even everything. As you remember from past chapters, each bounded context should be implemented as a project owned by a single team. However, shared kernels will be touch points between multiple bounded contexts, between multiple teams. Who owns the kernel? Everyone involved does. Understandably, this raises some alarm bells, as it goes against one of the major directives of domain-driven design, that of ownership. Due to all of the reasons explained before, it is important to know that shared kernels should be as small and contained as possible in order to reduce their surface area. The shared code must also be as stable as possible. The teams working on it should all have a high level of trust with each other, and in order to avoid catastrophic changes, each team modifying the shared kernel should have a good enough understanding on how the other bounded contexts both use and depend on the kernel's functionality. Therefore, it is paramount to understand that using shared kernels should be done as an exception, with grave consideration given to the costs it brings. With everything said thus far, you may consider shared kernels as an interesting idea, but one that has no real applicability due to its drawbacks. This is not the case. Kononov states that there are two main cases when using shared kernels makes sense. One, when the cost of duplication exceeds the cost of coordination, and two, when migrating legacy services piece by piece. Let's have a look at the first scenario, duplication vs coordination. If we go back to the authorization model figure, we are given a choice. We can choose to duplicate the authorization code inside both bounded contexts, or to create a common library shared between them. In this specific image, since we only have a couple of bounded contexts, duplication may make more sense, since the cost of maintaining it would theoretically be manageable. However, as the number of bounded contexts, and therefore projects, increases, the cost of maintaining said duplication increases exponentially due to the specific differences between each project. This is when the cost of duplication becomes too high, and it simply becomes easier to update a library version and coordinate said updates between the different contexts using a shared kernel. The second scenario is simpler. When modernizing a legacy application, like converting a monolith to a microservices architecture, for example, it is often impractical to migrate everything at once. In this case, one usually isolates a piece of functionality, which still depends on some parts of the monolith, and then deploys that isolated piece as a new project, or in other words, an independent bounded context. Over time, as pieces are migrated, the monolith becomes smaller and smaller, until there is no need for any shared functionality between the different contexts and the modernization is complete. The second type of collaboration is the customer-supplier. Unlike in the previous group, here there is an unbalance in the power dynamics between the supplier, also known as upstream, and the consumer, also known as downstream. This difference in power dynamics can be classified in three distinct patterns. 1. The conformist. Power balance favors the supplier, which has no real motivation to care for the consumer's needs. 2. Anti-corruption layer. Power balance favors the supplier, but consumer is not willing to conform, so it creates a barrier between the two, a layer that translates from the supplier's format to the consumer's. And last but not least, 3. Open host service. Power balance favors consumers. The supplier's main interest is to protect the consumers and keep them. The reason for this unbalance in power is usually the fact that suppliers and consumers can succeed independently from each other, like when you integrate with a third party belonging to a company different from your own. You both have needs, and collaborating increases your chance for success, but you exist separately, and each company has its own agenda. Starting with the first collaboration pattern on the list, the conformist, the client accepts the supplier's model, its bounded context, alongside its ubiquitous language. This may happen because the client has no choice, as the supplier may be a third party or due to internal politics. It may also be because the supplier's model is simply good enough or follows an industry standard. Regardless of the reasons for why this happens, the end result is always the same. The client conforms to the supplier's model and is dependent on it, relinquishing voluntarily its autonomy. This collaboration pattern often makes integrations easier and reduces complexity, as using the same model in both bounded contexts means they speak in the same language and can therefore work seamlessly together. On the other hand, as a result of this voluntary loss of autonomy, changes to the supplier's model directly affect the client, and if the client has a need for a specific type of optimization, it will have to convert the supplier's model, thus always obtaining a suboptimal solution. In short, this pattern works best when the client can assimilate changes from the supplier quickly or when the supplier's model is stable. It also helps when both bounded contexts have clear and distinct sets of responsibilities. With the second pattern, the anti-corruption layer, also known as ACL, the client does not accept the supplier's model, choosing instead to translate it into its own. Creating an ACL is usually desirable under the following circumstances. 1. When the client's bounded context contains a core subdomain. Core subdomains are the most important part of the business, and you usually do not want to couple that to a model that evolves separately and has a different set of priorities and problems to solve. 2. When the supplier's model is inconvenient or inefficient. If the bounded context of the client conforms to a mess, it too risks becoming one. And finally, 3. When the supplier's contract changes often. ACLs can also serve as a protection layer, a barrier that protects the client's model from the frequent changes in the supplier's contract. This way, when the supplier's contract changes, you only need to update the ACL and nothing else. For these reasons, ACLs can often be used when integrating with legacy systems or when the aim is to preserve the separation of concerns. However, because an ACL is an additional layer at the end of the day, it also comes with the natural downsides of adding more layers to an application, such as additional complexity, additional development time, and an additional point of failure for the system. The final collaboration pattern is the Open Host Service, also known as OHS. This pattern is unique in the sense that it is the only pattern where the power balance actually favors the client instead of the supplier. In this scenario, the supplier wants to accommodate to the client's needs in order to provide them the best service. This is usually useful when the supplier's model advances at a rate different from the public API it makes available to the users. It also allows the supplier to have different versions, the same API simultaneously, and also to have specific public APIs for some clients, all while maintaining its internal models protected. Much like the previous pattern, this one has the same benefits. It allows for a cleaner separation of concerns, and it enables bounded contexts to be developed independently. Additionally, it also promotes a service-oriented architecture and facilitates scalability. However, it also comes with many of the same drawbacks of adding an additional layer, and there can be performance penalties for the source if it has to translate a lot of requests to its many different clients. Because of this difference between the model the supplier has and the API it publishes, the public APIs used by the clients usually have the name of published language. This, however, is a statement echoed by the author and other authors in the space of domain-driven design, such as Pramanand Chandrasekaran and Karthik Krishnan, do have a different, more global definition of this term. For the purposes of this lecture, however, we will consider only the definitions provided by Vlad Kononov. And we have arrived at the time limit for this lecture. We have covered 2 of the 3 types of collaboration. Stay with us for the next one, where we will cover the remaining topics and end this chapter. My opinions and final conclusion will also be there. If you would like to see more content like this, then feel free to like, share, and subscribe. Wish you all the best, and I hope to see you again for the second part of this saga.